Welcome to Engineering Studio with Dr. Muhammad Tahir. In this video, we are going to discuss about the flexural behavior of compact beams. So first of all, bending stresses in a beam. So the bending stresses in a beam can be given by the elastic bending theory, which is sigma or F is equal to my over I. Here m is the applied bending moment, y is the distance from the neutral axis up to the extreme fiber or up to the required point at which we want to calculate the stress. I is the second moment of area of the section. For example, we have this rectangular section. So I will be equal to BH cube over 12. This is B and this is H. And Y will be the distance from neutral axis up to the extreme fiber or the point where we want to find this stress value. And if we rearrange this equation and we bring this y in the denominator, so it will become m divided by I over y, and we can write this term I over y as S, which is section modulus. So the stress will become m over S, applied bending moment divided by section modulus. Okay, so we can write the capacity of the section from this equation. So this is the stress, the value of stress that is produced in the member when it is subjected to bending moment. And if we know the stress value and we want to calculate the capacity, so we can rearrange this equation like this: m is equal to Fs. And if the stress is at the stage of yielding, so we can write that the capacity Mn is equal to Fys. So in this manner we can calculate the bending capacity of the section by using this elastic bending stress theory. Okay, next is the flexural behavior of a compact section. When a beam have adequate lateral stability of the compression flange, that its compression flange is continuously braced or braced at the intervals at the closer spacing that it will not buckle in the lateral direction. So in that case, the only stability limit that might limit the moment strength is the local buckling in the compression flange. So if we protect the lateral torsional buckling, then the only possibility will be that the flange can buckle or the web can buckle. So in case of internally compact section, so this second type of failure mode is also prevented, because we have seen in case of compact section when lambda is less than lambda p for both flange and web, so in that case the whole section can develop the yielding without any local buckling. So in case of internally compact section, so this the second possibility of failure is also prevented. So for internally compact section, even these type of instabilities do not occur and the section may reach the limit state of yielding. So the whole section can yield throughout the depth of the cross section. So the whole cross section will yield without any local instability or global instability of the member. So this is the case when the lateral torsional buckling is prevented. So in that case, compact section can yield throughout their depth. Okay, if we talk about the stress distribution in the compact section when it is subjected to bending moment, so with the increasing bending moment, the behavior will be like this. So for example, we have a W section. So if we apply the load, so at the initial stages, when the applied bending moment is less than my, the stress in the member will be less than Fy. So the member will be completely in the elastic range. So no part of the section will reach to the limit of yielding. So it means our section is in the elastic range. So if we further increase the bending moment or the applied bending moment, so some part or the extreme fiber of the member will reach to the stress value of Fy, mean they will reach the yielding limit state, and at that point the applied moment will be equal to my, and we can see in the section that the extreme fiber will be yielding. And in that case, the capacity of the section my, that will be equal to Sx times Fy. Sx is section modulus, elastic section modulus, and Fy is the yield stress of the section or yield stress of the steel. Okay, if we continue to increase the applied bending moment, so the interior fiber or the fiber underneath the extreme fiber will also yield. And if we continue to increase the applied loads, so the depth of this yielding portion will continue to increase. So the more and more fibers will yield. But the strength or the stress value will remain equal to Fy, because we know that in case of stress strain curve, so when the yield is reached, so the strain continue to increase but the stress value remains same. So here in the extreme fibers, the fibers which have yielded, the strain will continue to increase but the stress value will remain equal to Fy. And if we further increase the stress value or the applied bending moment, so a stage will come when the whole depth of the section will yield. So at that stage, the applied bending moment will be equal to My, which is termed as fully plastic or plastic moment, and the stress in the whole section will be equal to Fy. So in that case, the bending moment capacity Mp, which is termed as plastic moment, can be calculated by using this relation Fy times first moment of area of the section. So Fy times Zx. So Zx is actually the first moment area of the section. So by using this relation, Mp is equal to Fy times Zx, so we can calculate the capacity of the section that will be termed as the plastic bending moment capacity of the section. So at that stage, the whole section or the whole depth of the section will be yielding. So it is observed that the ratio of Mp over My is the property of cross section. So this ratio of plastic bending moment capacity and the elastic bending moment capacity, so these are the function of cross-sectional shape of the section instead of the material properties. So this ratio tells us how much the moment at a section can be increased beyond the first yield moment. So this My corresponds to the first yield moment when the only extreme fiber has reached the yield limit, and the Mp is the moment corresponding to the limit state when the whole section is yielded. This ratio is termed as shape factor and denoted by F. So F is equal to Mp over My, and if we write, so Mp is equal to Fy Zx and My is equal to Fy Sx. So the only term that we left with Zx over Sx. So the ratio of plastic section modulus over elastic section modulus will be termed as shape factor, and from this shape factor we can see that how much moment can be increased from the first yield point. Okay, once the plastic moment strength Mp has been reached, we have increased the bending moment and the stage has come when the whole section has been yielded, so the section can offer no additional resistance to the rotation, behaving as a fictitious hinge. So when the whole section is yielded, so at that stage the section will not resist any further moment. The moment will remain constant, but it will continue to deform or it will continue to rotate. And as it is continue to rotate at the section where the yielding of the whole section has been occurred, so that point can act as a fictitious hinge. It will act as a hinge. So this fictitious hinge is termed as plastic hinge, the hinge that is formed because of the plastic deformation of the section. So the combination of any three hinges, real or plastic hinges, so if in a member 3 hinges are produced, then the condition will arise that the member will become unstable, and that is termed as collapse mechanism. So any combination of 3 hinges, either real or fictitious or plastic hinges, if they combine in a member, the unstable condition will be reached and the mechanism will be termed as collapse mechanism. So here we see one hinge, second hinge and third hinge. So in that case, in a simply supported beam, if one plastic hinge is formed at the center, so the whole structure will collapse. And in case of fixed ended beam, if three plastic hinges are formed, then the structure will collapse.